We've been working on simplifying exponential expressions, and we're going to continue working on those today, focusing on positive, negative, zero, and integer exponents. So for our warm-up, we'd like you to evaluate the following expressions. Now, in thinking about the expressions and the meaning of them, we know that the exponent tells us how many of the base that we're working with. So many of you know that 3 to the third means that we have 3 threes being multiplied together, and 3 times 3 times 3 is 27. 3 to the second means you have 2 threes being multiplied together, so 3 times 3 is 9. And 3 to the first means you have a single 3, so we have our answer of 3. We also don't want to forget that we're working with these values. We're talking about the base, how many of what we have based on what the exponent is telling us. But 1 is always a greatest common factor of those. So if we think about that another way, remember it's really 3 to the third, 1 times 3 times 3 times 3, 3 to the second, 1 times 3 times 3, and 3 to the first is 1 times 3. So when we go to evaluate something like 3 to the power of 0, that's telling you that you have none of the base. But what do you still have to work with? Well, we have a 1. So 3 to the power of 0 is equal to 1. Now, oftentimes at this point, people tend to grab the calculators and enter in the next 3 to see what their values are. And so if you did that, you saw that 3 to the negative first was equal to 0.3 repeating. 3 to the negative second, you got 0.1 repeating. And 3 to the negative third was 0.037 repeating. Well, again, what is the meaning of all of this? Well, if you think about some of these decimal equivalents, you should recognize that 0.3 repeating is 1/3. So how can we use that to think about what does 3 to the negative 1 power mean if the value is 0.3 1/3? Well, that means there's a 3 in the denominator. So we could think of 3 to the negative third as 1 over 1 times 3, get our 1/3. Again, 1/3's decimal equivalent is 0.3 repeating. Now, if we use that same idea for our next two expressions, 3 to the negative second, well, that means I would have 2 3's in the denominator. So it'd be 1 over 1 times 3, which would be 1/9. That decimal equivalent is 0.1 repeating. 3 to the negative third power would mean that you have 3 3's in the denominator being multiplied together. So we've got 1 over 1 times 3 times 3 times 3, which is 1/27. That decimal equivalent was our 0.037 repeating. So now we don't have to grab our calculators to evaluate these exponential expressions, especially when we have negative exponents, because we can see the pattern that's resulting. When you have a negative exponent, it's telling you that the base is in the wrong location. All of these were written as the bases are in the numerator, but because the exponent is negative, it's really telling you that it belongs in the denominator, and that's how many that you have in that location. If you had a negative exponent in the denominator, again, it's telling you it's in the wrong location. It really belongs in the numerator. So we can use those patterns to help us simplify our exponential expressions. So the two new ones that we saw based on these was when we had a power of 0, it always resulted in 1, because 1 is a greatest common factor of every value. And again, your base has to be a number other than 0 as well. And again, when we saw that we had a negative exponent, it was telling you it was in the wrong location. So if something was written in the numerator as being having a negative exponent, it really belongs in the denominator. And again, that base has to be a number other than 0. So let's try using all of our patterns that we've seen with simplifying our exponents and doing some simplification with a couple of more examples. So what we want to do is try working on simplifying these exponential expressions. And so for number 1, we have negative 7x to the third. And we want to think about, well, is everything as simplified as can be? And we do see a negative here. And you have to be careful. The negative is with the coefficient of 7. not with the exponent. Therefore, we're not going to be moving anything to the denominator. It is what it is, and it's in the right location. And as we look at number 1, there's nothing else that we can simplify, so we're going to leave it as negative 7x to the third. Now in number 2, we've got 17x to the negative fourth, y to the second. And your eye should be drawn here where you have x as the base and you've got the power of negative 4. That power, since it's negative, is telling you that it belongs in the denominator. So let's rewrite it where it belongs and see if there's any more simplifying we can do. So we should have 17y to the second divided by x to the fourth. And again, we're looking to see, do we have any greatest common factors that we could simplify and divide out? And we don't. We don't have common bases here. 17 only has factors of 1 and 17, so there's nothing that we could divide out there. So this would be our final result. Let's take a look at a couple more. So for number 3, we've got negative 8, x to the third, y to the negative second, and z to the negative fourth. So as we look at this exponential expression, hopefully your eyes are being drawn to your y and z base because they have exponents with negative values, and that's telling you that they're in the wrong location. They don't belong in the numerator, they belong in the denominator. So let's rewrite the expression so that they are where they belong. And then look to see, do we have any greatest common factors that we could divide out? And with our exponents, our bases are x, y, and z, and none of those are in common that we could look for dividing out any common factors there. And our coefficient of negative 8, we do have a coefficient of 1 here, but that's not going to change anything. So this would be our simplified exponential expression. As we look at number 4, we've got 6w to the negative fifth, z to the fourth, divided by 2, y to the negative third. And we should spot a couple of things right away. We can see that w is raised to the power of negative 5. So that's saying, hey, I'm in the wrong location. I really belong in the denominator. And we also see that y is raised to the power of negative 3. And again, I'm in the wrong location. I really belong in the numerator. So if we rewrite those in the correct locations, let's see if there's any simplifying that we can do by dividing out greatest common factors. And as we can see with our variables, the bases are not like, so there's nothing that we can really simplify there. However, we do have the coefficients of 6 and 2. And 6 has greatest common factors of 2, I should say greatest common factors of 2 and 3. And then we have our coefficient here of 2 that has a common factor of 2 and 1. So we have a greatest common factor of 2 that we could divide out from both 6 and 2. Well, 6 divided by 2 is 3, and 2 divided by 2 is 1. So we're going to have 3 in the numerator, z to the fourth, y to the third, over our 1, w to the fifth. So our final expression would be 3z to the fourth, y to the third, divided by w to the fifth. You can also write the numerator as 3y to the third, z to the fourth, over w to the fifth. Some mathematicians like writing the variables in alphabetical order, and again, it's still the same element, so it would be the correct simplification. Let's try simplifying these two expressions. So for number 5, we have negative 12 m to the third n to the fifth divided by m to the negative fourth. And as we look at this expression, our eyes should be drawn immediately to the denominator where m is raised to the power of negative 4. Again, that negative exponent is telling you that it's in the wrong location. It really belongs in the numerator. So let's rewrite it to where it belongs and see what kind of simplifying we can do. So notice we no longer have a division problem, and we're going to look to see, do we have any like terms that we can combine? And so notice how you have m to the third and m to the fourth. Well, there are 3 m's here and 4 m's here. That means we have a total of 7 m's. So we could rewrite this as negative 12 m to the 7th, n to the 5th. Then for number 6, we have x to the 4th, y to the negative 7th, divided by x to the 4th. And our eyes should be drawn here. We can see that y is being raised to the power of -7, so it doesn't belong in the numerator, it belongs in the denominator. So if we rewrite it where it belongs, now we've got x to the 4th divided by x to the 4th, y to the 7th. Because it's a division problem, we're looking for greatest common factors that we can divide out. And we can see that we have bases of x's in common. There are 4 x's in the numerator and 4 x's in the denominator. So we have greatest common factors of x, 4 sets of them that we could divide out. So those x to the 4ths will divide out, and we're going to be left with y to the 7th in the denominator. And this is important. When we're dividing out those greatest common factors, you're left with a 1 in the numerator and just y to the 7th in the denominator. So that would be our simplified expression, 1 over y to the 7th. Let's try another one. Here we want to simplify this exponential expression. So the first thing that we can see is that we have all of this raised to the 3rd power, which means we have 3 sets of the inside. Now, you might have also noticed that we have some negative exponents within our quantity. So there's a couple ways we can do this. The first thing we could address is the negative exponents and rewriting them to where they belong. So this x to the -2nd really belongs in the denominator, and this z to the 7th really belongs in the numerator. So if I write them where they belong, again, we do a quick scan of the numerator. There are no like terms that we can combine here, so we're okay. But in the denominator, notice how you have x to the 5th times x to the 2nd. That's a total of 7 x's in the denominator, so we can rewrite that as x to the 7th. So now that the numerator and denominator are simplified and everything is where it belongs, we can start working on the 3 sets of the inside of our quantity. So that means we're going to have 3 sets of 4, 3 sets of y to the 4th, 3 sets of z to the 7th, and 3 sets of x to the 7th. So remember, 3 sets of 4 would be 12, and 3 sets of 7 would be 21, and 3 sets of 7 again is 21 in the denominator. So again, as we're looking, everything is simplified in terms of y, z, and x, but we know 4 to the 3rd is a value. This is saying we have 3 4's being multiplied together. 4 times 4 is 16, and 16 times 4 is 48. So our simplified value here, sorry, not 48, 64. So we have 64 y to the 12th, z to the 21st divided by x to the 21st. That would be our simplified result from our exponential expression above. Now we started this one by addressing the negative exponents first. However, you could have worked with the 3 sets first and then rewrote the negative exponents where they belong. So if you did it that way, taking 3 sets of everything on the inside, you'd have 4 to the 3rd, x to the -6th, y to the 12th, divided by x to the 15th, z to the -21st. Again, we can address the negative exponents, so the x to the -6 should go to the denominator, and z to the -21st should go to the numerator. Here we can see in the denominator, we have x to the 15th and x to the 6th. 15 and 6 is a total of 21, so we have x to the 21st there. And then we could work on doing our 4 to the 3rd, giving us our 64. So notice we're going to end up with the same simplified expression, regardless of whether you started with addressing the negative exponents on the inside of the quantity first, or working on the 3 sets of the quantity and then going from there. Let's try one more. Let's simplify our expression here. We've got 2y squared divided by x to the -3rd, all raised to the -2nd power. Now in this problem, again, there are 2 approaches you can take. First thing, you might have looked to see that we do have some negative exponents, and we can see that our grouping symbol here on the exterior of that, we have the power of -2. So again, it's telling you that things are in the wrong location. And because it's on the exterior of the grouping symbol, it's saying everything within is in the wrong spot. So we're going to put everything where it belongs. The denominator is becoming the numerator, and the numerator is becoming the denominator. So we put everything where it belongs based on that grouping exponent. Okay, so it's still everything to the power of 2. Now, if we look again, we can see we have x to the -3rd in the numerator, and we know that that's still in the wrong location. It belongs in the denominator. So if we put it where it belongs, now we have 1 over 2y squared x to the 3rd. Or if you wrote it as 2x to the 3rd, y to the 2nd, that's still the same expression. We have 2 sets of what's on the inside. So that would mean we've got 1 to the 2nd power, and 1 times 1 is 1. We have 2 sets of 2, so that would be 2 to the 2nd, which would be 4. We have 2 sets of y squared. Again, that means a total of 4 y's. And 2 sets of 3 x's, which would be a total of 6 x's. So we can look at this, and like we said, we simplified it. It would be 1 over 4, and if you want to do alphabetical order, x to the 6th, y to the 4th, that would be a simplified version. If you wrote it as 1 over 4, y to the 4th, x to the 6th, it's the same expression. And again, this approach was tackling the negative exponent on the outside of our grouping symbol, telling us everything on the inside was in the wrong location to start, so we switched the numerators and the denominators. Then we addressed if we had any remaining negative exponents within our quantity, and then we did the 2 sets of what's on the inside. Now, the other approach was rewriting what was on the inside of the, not writing on the side. Some of you just said, well, I know I have -2 sets of the inside, so perhaps you distributed the -2 to each base of your quantity. And then you thought about locations of those bases. So because we have a -2 for the exponent on the base of 2 and a -4 on the base of y, they really belong in the denominator. And then we can simplify from there. 2 to the 2nd power, we know is 4. We've got x to the 6th and y to the 4th. So again, it's bringing us back to our simplified expression of 1 over 4x to the 6th, y to the 4th. So you can see as you're simplifying your exponential expressions, we can implement the patterns that we've seen to accomplish that goal. And there may be a couple of different approaches to take that will still result in the same simplified expression. So now it's going to be your turn to practice implementing your exponential simplification patterns. And we're going to see your progress from there.